as I mentioned before, for speaker embedding based speaker verification with neural networks, the first step is to train a speaker classification system, right. So, here for the purpose of getting X vectors, the speaker classification system that is used is made of TDNNs. TDNNs are time delayed neural networks, okay, neural networks, and TDNNs are usually made of, TDNN blocks are made of this con 1D blocks, some activation function and a batch normalization. Con 1D I am sure it was discussed in the convolution neural networks module, so you can go and brush it up a bit. So, here this input is some MFCC features, okay, say it is some 36 and there are frames, right. So, there will be some T frames, 36 cross T, okay, this I am just assuming, okay, it is not a given number. So, it is given to the first TDNN block. As mentioned before, TDNN blocks are made of 3 stuffs, one is con 1D blocks, then an activation function and then a batch normalization. Here you see this in the square bracket, right, T minus 2 and T plus 2. This actually means your kernel size is 5 because you take T minus 2, T minus 1, T, T plus 1 and T plus 2, right, all 5 frames are taken, correct. So, the kernel size is 1 and there is no skipping, right, T minus 2, T minus 1, T, T plus 1, T plus 2, there is no skipping. So, the dilation is just 1, okay. So, that is the meaning of this bottommost block. But if you go to the second block, TDNN2, it is enclosed in flower braces, that actually means you take T minus 2, T and T plus 2, only 3 frames. So, there is a skipping, right, because after T minus 2 you directly go to T, you are not worried about T minus 1. Similarly, after T you are not worried about T plus 1, you directly take T plus 2. So, the dilation here is 2. Similarly, in your TDNN3 block, it is enclosed in flower braces, which actually means I take T minus 3, T and T plus 3. So, the dilation here is 3. Here I am just taking the Tth frame, so no problem. TDNN5 also I just take the Tth frame, no problem, okay. So, until this part, this is called your encoder, okay. Then you do something called a start spool. After this TDNN5, you end up getting a 1500 cross T, okay. There are T frames and each frame is 1500 dimensions. That is what you end up after you move past the encoder. Then comes the start spooling layer. What the start spooling layer does is, it calculates the mean across the frames. There are T frames, right. So, across the frames when you calculate, for each dimension you will get a mean. So, the mean becomes a 1500 cross 1 vector and the standard deviation is also computed, that also becomes a 1500 cross 1 vector. When you just stack them together, it becomes a 3000 cross 1 vector and it is given to a feed forward, 2 feed forward neural networks FFNN1, FFNN2 and then finally a linear layer which projects it to the number of speakers. Assuming I take 7000 speakers, if I have 7000, speakers, then this is going to be 7000 cross 1, okay. And finally what I do, I take a softmax and a cross entropy to just classify which speaker this utterance belongs to. This is how your speaker classification network is trained. Once it is trained, what is the next step? The step 2 is to get an embedding. How do we get an embedding from this? What people do is, we know that a feed forward is made up of a linear layer, some activation function, some normalization, okay. So, embeddings are tapped from the linear layer after it is completely trained. Okay, when you want to get an embedding for an utterance, you pass that utterance to this trained network and you tap just after the linear layer of FFNN1. As you know, the input to FFNN1 is 3000 cross 1 and the output of FFNN1 is 512 cross 1. What will be your embedding dimension? The embedding that you get will be of dimension 512 cross 1 because your linear layer would have projected it to 512 cross 1. Okay. So, that is how you tap your embedding for X vectors. So, that this linear layer is also called as an affine layer. Okay. Next vectors are R vectors. R vectors, they have received the name R vectors because they are obtained from ResNets. Okay. The speaker classification architecture previously was made of TDNNs, which are time delayed neural networks. Here the architecture is ResNets. ResNets you might have come across in your other courses, in deep learning course I suppose. ResNets are useful in image classification. Okay. And they are made up of con 2Ds. The difference between the X vector architecture and this architecture is that the previous architecture used con 1Ds and the R vectors architecture uses con 2Ds. There are different ResNet architectures. Okay. For an example, I have just taken some ResNet 34 architecture here and I will show you how an embedding is tapped from this architecture. So, I just want to show what an ResNet block looks like. So, this is how your ResNet block look like. Okay. This is one con 1D, con 2D. This is also a con 2D. Okay. And then you have this connection. Okay. These are called residual connections. So, the name ResNets, they are also called as highway networks. With the invention of these networks, training of deeper neural networks became a success. Previously, people were struggling to train deeper neural networks. So, with this skip connections added, it became easier for them to train very deep neural networks. So, we saw what a ResNet block looks like. Okay. So, this ResNet 34 is made of these many blocks. Input is a 40 cross 200 in the sense the frames are fixed here. Okay. Previously in your con 1Ds we had the freedom, the frames T they can vary, but here it is fixed. 40 cross 200 cross 1, and when you use a con 2D with a 3 cross 3 kernel size filter and stride 1, you get 40 cross 200 cross 32. In the sense, how many filters there are? 32 filters. Only then you will end up with this output from con 2D 1. Okay. And then it is given to ResNet block 1, which is actually repeated 3 times. Okay. So, because you saw here, right, in a ResNet block you have 2 con 2Ds. So, the 2 con 2Ds are made of 32 filters and of kernel size 3 cross 3, stride is 1, and the residual block 1 is repeated 3 times, which results again into a 40 cross 200 cross 32. In your second block, the number of filters are increased to 64, and because of the stride there is a reduction in the dimensions. You have to notice this, 40 and 200 became 20 and 100, and due to the increase in the number of filters your output is also increased. ResNet block 3, 128 filters, stride is again 2, so again there is a reduction from 20 to 10 and from 100 to 50, and because 128 filters you will get 128 in the third dimension. Similarly, after your ResNet 4 you get this. Okay. So, this means what? There are 256 channels, 5 dimension, 25 frames and 256 channels. When I do stats pooling, there is going to be 256 channels as such. This 5 cross 25, right? So, I do the pooling across the frames, right? How many frames are there? 25. And the dimension is 5. So, I have a mean and a standard deviation to be calculated. So, mean I will get 5 cross 1 or I should say 5 cross 256, and standard deviation I will get a 5 cross 256. Both put together I will get a 10 cross 256 after stats pooling. When I flattening it, it's just stacking them together. I'll get 2560 elements. Dense layer 1 is nothing but a feed forward network which brings the 2560 to 256. Another dense layer which projects it to the number of speakers in the whole set of utterances. So, this is how the architecture is. You train this model, again you will tap it somewhere here, tap the embedding here from the affine. You will get a 256 cross 1 embedding. So, this is about your R vectors. So, R vectors considers speech, the features, right? It takes them or consider them as images and works on them. Okay. That is about R vectors. So, we have seen this ResNet block already. Next, let us move on to the S vectors. As I mentioned before, this is by IITM. Using transformer encoders, you must have come across transformers in the previous lectures. So, transformers are a new, okay, I should not say completely new, there are other variants that have already come. So, a transformer has an encoder, a decoder, okay. Its major strength is this attention, self-attention. Okay. So, why is this a major strength? Because at a given time it is able to look at all the frames, but when you take convolutions or other networks, only few frames are given to it at every stage and the context is limited in the initial stages. As the depth increases, the context increases. But in transformers, what happens is that at every layer, each frame is able to look at all the frames and gather some information. That is where the strength of the transformer is lying. So, what we thought is, because it is able to look at all the frames at one go in every layer, why not use this encoder, the transformers encoder, as the encoder for the classification architecture. So, these are the encoder layers which are actually some kind of modified transformer encoder, okay. We just changed the normalizations here and rest remains the same, okay. Only the encoder part we changed to the transformer encoder. And speaker embeddings we extracted it from FFNN3, from the affine part which is actually just after the linear transformation. So, the embeddings here are of dimension 512 cross 1. So, you add position embeddings just like a transformer encoder would do, no change, just change this encoder part. So, once this is done, we have to extract the vectors, right. I said it is extracted from this FFNN3. But one thing to be noted is, because of this position embeddings, when you have trained, let us say your number of time frames were all lesser than some 500 frames, okay. So, position embeddings, it would know till 500, it would have an idea, okay, this is the position embedding for 500 and the network would have also trained, okay. Now for extracting the vectors, if the utterance was greater than 500, because the model would have not seen such positions, there is a problem. So what we do is, if it is greater than 500, okay, we will chunk it as smaller sets, okay, C1, C2, Cn, which is chunk 1, chunk 2 and chunk n. You give it to the model and you will get the vectors, the embeddings. So if there are 5 chunks, you will get 5 vectors. Finally, you average them to get the final vector. This is how the complete S vector extraction is done when the input utterance length is greater than what your trained utterance lengths are.